Good day, everyone. Welcome to RICHFIELD Hybrid Learning. My name is Silas Toperesu, and I'm your lecturer for Mathematics 512 module. Today, we're going to look at our syllabus topic for Lecture 2 for differentiation. On the learning outcomes of this topic, upon completion of the study of this chapter, you will be able to demonstrate an ability to differentiate any trigonometrical function using the differential rules such as power rule, product rule, quotient rule, chain rule, as well as implicit rule. You will also be able to develop an ability to find the derivative of trigonometrical functions such as sine, cosine, tangent, sec, and cosec, as well as cot. Let's now look at the properties of a trigonometrical functions. In a trigonometric functions, differentiation of a trigonometrical functions is defined as a mathematical process of determining the rate of change of a trigonometrical functions with respect to a variable angle. The basic trigonometrical functions include the 6 main trigonometrical functions, which is the sine, cosine, tangent, cotangent, secant, as well as cosecant. All the derivative of trigonometrical functions are derived from our 6 main basic trigonometrical functions. So the derivative of the 6 main trigonometrical functions are as follows. The dx or derivative of sine x is equals to cos x. So all the derivative of any sine x will give us the cos x. And the derivative of cos x is equals to minus sine x. And the derivative of tan x is equals to sec squared x, and then the derivative of cot x is equals to minus cosec squared x, and the derivative of sec x is equals to sec x tan x, and the derivative or differentiation of cosec x is equals to minus cosec x cot x. So all other derivative functions will be derived from these 6 main basic functions of trigonometrical. Let's now look at some of the examples of finding the derivative of trigonometrical functions. We have our first example that is saying, find the derivative of y is equals to cos 3x. From our differential rules, we know that the derivative of cos x is equals to minus sine x. But in this case, we have got y is equals to cos 3x. We don't have an x in front of cos, but we have got 3x. So we can use a chain rule to differentiate to let u is equals to 3x. So what it means when you're applying a chain rule, it means we differentiate a function that is in front of our function cos x. We differentiate a variable which is 3x. So when you differentiate the variable in front of cos x, which is 3x, we're going to get the value of 3. So the result that we're going to get, which is 3, we multiply it with the derivative of a function of cos. So the derivative of a function of cos is equals to minus sine x. So we multiply 3 times minus sine. In place of x of our result, since we're differentiating, we're not differentiating cos 3x, but we're not differentiating cos x, but we're differentiating cos 3x, which means our result also is going to have minus sine 3x. So we now have our final result of our differentiation of y is equals to cos 3x is minus 3 times sine 3x, which gives us minus 3 sine 3x as our derivative result of this function. Our second example is also saying find the derivative of y is equals to sec 5x. We know from our 6 main differential rules, which states that the derivative of sec x is equals to sec x tan x from our trigonometrical rules. But now in front of sec we have got 5x. So we have to differentiate the variable that is in front of sec x, which is 5x. So when we differentiate 5x, we're going to get the result, which is 5. And then the result that we're getting, we multiply it with the derivative of our function of sec. So our derivative, the derivative of function sec is sec and tan. So now we multiply 5 times sec and tan. But in place of x in our sec, we replace it with 5x because we have got 5x here. In our sec, we don't have x. So the derivative of sec 5x, we are going to get sec 5x tan 5x, which is now our final result of the derivative of y is equal to sec 5x. We have got 5 sec 5x tan 5x. Our third example here is also says, find the derivative of y is equals to 2x to the power 5 minus tan 2x plus 2x squared. So here, if we apply the differential rule, which is the constant multiplication as well as the power rule, and the addition and difference rule, we're going to differentiate each term by term. So when you differentiate each term, our focus now is going to be on our trigonometric function, which is tan 2x. So when we are differentiating tan 2x, we know from our 6 main differential rules that the derivative of tan x it is equals to sec squared x from our trigonometric rules. So when we are differentiating then tan x, we're going to differentiating a term which is the variable in front of tan, which is 2x, and get the result of 2, and then we say 2 times the derivative of a function of tan, which is the result of the derivative of tan, which is sec squared, and in place of x, we put now the variable that we have, which is 2x. So the result is going to be 2 times sec squared 2x. And then the first term, which is 5 to 2 to the 2x to the power 5, when we're differentiating using the power rule as well as the constant multiplication rule, we're going to take the power and then we multiply with the term that we have, which is 2 times 5. Then we subtract 1 from the power, so we end up having 5 times 2x to the power 5 minus 1 by the power rule as well as the constant multiplication. And then our last term, which is 2x squared, when we're differentiating this term, we use also the power rule and the constant multiplication, which means we take the power, which is 2, and then we multiply with it and say 2 times 2, then x to the power 2 minus 1, we subtract 1 from the power. So we end up having 2 times 2, x to the power 2 minus 1. And now we solve 5 times 2, which gives us 10. Then x 5 minus 1 gives us x to the power 4. Then 2 times sec squared 2x, we're going to get minus 2 sec squared 2x. Then 2 times 2x to the power 2 minus 1, we're going to get 4x. So our final result with this, with the derivative of y is equals to 2x to the power 5 minus tan x plus 2x squared, is going to be the expression of 10x to the power 4 minus 2 sec squared 2x plus 4x. Let's look at our fourth example that says find the derivative of y is equals to x cubed cot x. So if you look at our function that we have now, it consists of two functions that are multiplying on each other. The first function is x cubed and the second function is cot x. So we can apply the product rule when we differentiate this function. So we can label our first function as our function of fx and the second function is our gx. And then we need also to apply the differentiation rule of trigonometrics, which states that the differentiation of cot x is equals to minus cos x squared x. So automatically we know from our differentiation rule of trigonometric that differentiation of cot x is equals to minus cos x squared rule. So when you apply our product rule, we know that we take our fx, our gx, then we say gx times the derivative of our fx, which is x cubed, then plus fx, which is x cubed, times the derivative of our gx, which is cot x. They will substitute in our product rule formula. And now we have to find the derivative of our x cubed. The derivative of x cubed, we need to use the power rule. When we use the power rule, we're going to say 3 times x to the power 3 minus 1, which is the result of our derivative of our x cubed. And then when we substitute to find the derivative of cot x, derivative of cot x from our differential rule is equals to minus cos x squared x. So the derivative of cot x is equals to minus cos x squared x, which is multiplied to x cubed. So we end up having our final result as cot x times 3x to the power 3 and minus 1, which gives us 3x squared cot x, and x cubed times minus cos x squared x, which gives us x cubed cos x squared x. So this 3x squared cot x minus x cubed cos x squared x becomes our result of derivative of this expression, which is y is equals to x cubed cot x. Here is the fifth example of solving a trigonometric function. You have the question that is saying find the derivative of y is equal to sine to the power 5 2x squared. So when you have got an expression trigonometric function in this format, sine 5 2x squared is the same as sine 2x to the power 2 to the power 5. So we can change this and put in bracket and say everything to the power 5. That's exactly what it means. So when we find the derivative of such an expression, we need to use the chain rule. So we let u is equals to the inner function, which is sine 2x squared. So u is equals to sine 2x squared, and then we let y, which is the outer function, which is y is equals to u to the power 5. So now we differentiate our inner function, which is du dx, u in terms of x. So when we're differentiating our inner function, we need to differentiate differentiating the variable that is in front of our trigonometric function or a function which is sine. So when you differentiate 2x squared, we use the power rule and say take the power and say 2 times 2x to the power 2 minus 1. So the derivative of our variable that is in front of our trigonometric function is going to be 2 times 2x to the power 2 minus 1. Then the derivative of our sine x from our differentiation rule, derivative of sine x is equal to cos x. So the derivative of our sine 2x squared is going to be cos 2x squared. So when you multiply 2 times 2x to the power 2 minus 1 times cos 2x squared, you are going to have 4x cos 2x squared is our derivative of our function, which is u equals sine 2x squared. So we're differentiating also our outer function, which is y is equals to u to the power 5. So when you find du, dy du, we're going to use the power rule and say 5 u to the power 5 minus 1, and we end up having our result as 5u to the power 4. Since now we have the derivative of our inner function as 4x cos 2x squared and our derivative of outer function as 5u to the power 4, we now need to find our dy dx. So our dy dx is supposed to be 2 du dx times dy du. So when we say du dx times dy du, our du is going to cancel each other, which is the one on a numerator and the one on a denominator. So we're going to left with dy dx. So now we substitute on place of du dx with our derivative of du dx, which is 4x cos squared. Then we say multiplied by dy du, which is our derivative of dy du, which is 5u to the power 4. So when we multiply, we're going to get 20u to the power 4 cos 2x squared. And now we'll return the actual value of u, which is sine 2x squared in place of u. So when we return the actual value, we're going to have our final result of the derivative of 20 sine 2x squared to the power 4 cos 2x squared is our final result. Let's now look at the differentiation of exponents and logarithms. Exponent function and their corresponding inverse function, which is logarithms functions, have the following differential formulas, which is the one. So these are mainly 4 properties that we should know when we're differentiating exponents. And exponents and logarithms are inverse of each other. So the 4 properties are as follows. The first one, if we have got a function fx which is equal to exponent x, then the derivative of any exponent x is equal to exponent x. So what it means if we have got an exponent to the power x, when we have got x here, we differentiate the x, which is a power, and then with the result we multiply it with the same exponent of that exponent x. So that's how we find the derivative of our exponent x. That is property 1. The property 2, if we have a function fx which is equals to a constant to the power x, where a, which is our constant, is greater than 0 and a is not equal to 1, then the derivative of such an exponent or such a function is equals to a, which is our constant to the power x, times ln a. So that's how we differentiate any function that you've got a constant to the power x. Then the third property is, it says, if fx is equal to ln x, if we have the function that is fx which is equal to ln x, then the derivative of such a function is equals to 1 over x. In other words, it means when you're differentiating such a function that you've got a ln expression, we need to differentiate an expression in front of a ln, then the results that we are going to get, then we say the results divided by the original expression which is in front of ln, which is x. So if you are differentiating x, I'm getting 1. So once you get 1, then we say 1 divided by the original expression which is in front of ln, which is x. So that's how we differentiate a ln x. Then the fourth property is saying if fx is equals to log x in base a, so log x in base a, where a is greater than 0 and a not equal to 1, then when we differentiate such a function, we need to differentiate the variable or expression that is in front of our log, which is x, and then we say the result divided by x, which is our expression, times ln a constant which is a base value. Let's now look at an example of solving a function, finding the derivative of our exponent function. So here we've got the question that is saying, find the derivative of fx is equal to exponent x to the power 4 minus 2. So when we find the derivative of such an expression, we need to write the whole expression, the original expression as it is, which is exponent fx to the power 4 minus 2. Then we multiply this original function with the power, the derivative of our power of exponent, which is x to the power 4 minus 2. So when we find the derivative of our power of exponent, which is x to the power 4, we use power rule on x to the power 4. So when we use power rule, we are going to have 4 times x to the power 4 minus 1. Then we find also the derivative of our constant, which is minus 2, of which, using the constant rule, we're going to get 0. So we end up having 4x to the power 4 minus 1 times our original expression of our fx, which is reduced to the value of 4x cubed exponent x to the power 4 minus 2 as our final result of derivative of our fx. Then we also have a second question that is saying, find the derivative of y equals ln sine x. So when we're differentiating an expression that you've got a ln, we need to differentiate an expression that is in front of a ln. So the first thing that we have to do, we have to say 1 divided by our original expression that is in front of a ln, which is 1 divided by sine x. Then we say times derivative, which means we derive the expression that is in front of our ln, which is sine x. So we find the derivative for sine x, which is did x for sine x. So from the trigonometrical rules of differentiation, we know that the derivative of sine x equals to cos x. So our result is going to be cos x times 1 over sine x, and we are going to get cos x divided by sine x, which reduced to cot x, because from the trigonometrical identities, cos x divided by sine x is equals to cot x. Here is our third example that says, find the derivative of y is equal to 3 to the power 2x minus log x cubed in base 5 plus exponent minus 3x squared. So to solve this, we need to solve term by term. We need to differentiate each and every term. So when you're differentiating the first one, since the first one is 3 to the power 2x, a constant to the power 2x. So from the rules and laws of logarithms, we know that when you're differentiating any constant to the power an expression, we need to differentiate, we need to take the expression as it is, which is 3 to the power 2x, and then we multiply with the ln of what? Of ln x, and then we differentiate also the power, that is the power of our expression. So now we need to say 3 to the power, which is our 3 to the power 2x, the fx expression as it is, then we say times ln our constant, which is 3, then times the derivative of our power, which is derivative of 2x, which is going to give us 2. So the second one, which is the log, using the log laws, we know that when you're differentiating anything that have got the log, we have to say 1 divided by our expression of x cubed ln our base constant, which is base 5. Then we say times the derivative of our expression, which is the derivative of x cubed. Then we say plus on an exponent. When we're differentiating an exponent, we know that we need to take this exponent exactly as it is. Then we say times the derivative of the power of our exponent, which is derivative of minus 3x squared. So when you're differentiating the first term, we're going to have 2 derivative of 2x, we are going to get 2, which becomes 2 times ln 3 times 3 to the power 2x. Then minus on the ln, we're going to have derivative of x cubed using the power rule. We're going to have 3x 2 minus 3 minus 1, which reduced to 1 over x cubed ln 5 times 3x to the power 3 minus 1. Then the third term is going to be the exponent, which is the derivative of minus 3x squared. Using the power rule and the constant multiplication, we're going to have 2 times minus 3x to the power 2 minus 1 times our original expression, which is exponent minus 3x squared. So our answer is going to be reduced to 2 ln 3 to the power 2x minus 3, our derivative multiplied by 1 over x cubed ln 5 is going to be 3x squared divided by x cubed ln 5, minus, when we multiply the third term, we're going 2 times minus 3x x to the power 2 minus 1 times our expression of exponent, we're going to get minus 6x exponent minus 3x squared. So our answer is going to be reduced to 2 ln 3 3 to 3 to the power 2x minus 3 over x ln 5 minus 6x exponent minus 3x squared is our final result of the derivative of our function y is equal to 3 to the power 2x minus log x cubed to the base 5 plus exponent minus 3x squared. Let's now look at implicit differentiation. The method of implicit differentiation allows us to find the derivative of implicit function. All functions that we have been differentiating so far are explicit functions. So the technique of implicit differentiation allows us to find the derivative of y with respect to x without having to solve the given equation for y. Implicit expression is a composition of functions, so we use the chain rule to differentiate such expressions. Here is an example of implicit function. So the question here is saying differentiate x to the power 2, y to the power 3 minus xy is equals to 8. So when we're differentiating in implicit function, we need to differentiate each and every variable at each and every value or each and every term. So here, if you check on the first values, we have got variable y and variable x multiplied to each other. So we need to use a composition. We treat this as two different functions, which is function 1, which is x squared, and function 2, which is y squared. So we can use a product rule to differentiate any two functions that are multiplying on each other. So when you apply the product rule of differentiation here, we're going to take the first one is our fx. So we say fx times the derivative of our gx, which is y cubed. So whenever we are differentiating y, we need to represent it with a dy dx. So we are saying dy dx of derivative of a y function. Then we say plus our gx, which is y cubed, times the derivative of fx. So that's the power rule, the product rule of differentiation that we're applying on our first term. Then the second, we also have minus xy. Xy have got also two functions, which is x and y. So we use also the product rule. So when we use the product rule, we treat the first as our fx and the second our gx. So now we are saying fx times the derivative of gx, which is derivative of y, plus the gx, which is y, times the derivative of what of fx, which is derivative of x, is equals to derivative of 8. So 8, we are differentiating a constant. So derivative of 8 is going to give us a 0, which is a constant. But now we need to solve for the derivative of a product rule. So here we have got x squared, derivative of y cubed using the power rule. We are going to say 3 times y to the power 3 minus 1, which is the value of the derivative. And the second one, which is a differentiating x to the power 2, we use the power rule, and we're going to have 2x to the power 2 minus 1. And the derivative of y only, which is only y value, we're going to have 1. And the derivative of x1 only, we're going to have 1. So we end up having our dy dx. So wherever we are differentiating in y, we need to keep that dy dx. We don't remove it. But when we are differentiating in x, we can actually evaluate it to an actual value of x. So when we are differentiating in y here, we keep our dy dx. And on the second one, we're differentiating in x, so we're going to have the value of x. And here on this term, we're differentiating in y, we're going to keep our dy dx. So if you're differentiating your y, you need to keep your dy dx. So here we're differentiating in y, so we multiply now. When you say x cubed to remove the bracket, so we're going to get x cubed, x to the power x squared times y to the power 2 plus 2, which is y cubed times 2x to the power 2 minus 1, which gives us 2xy to the power 3. Then the third one, we have got x times 1 dy dx, which is minus dy dx x minus 1 y times 1, it gives us minus y. Y times 1 times this negative is going to be minus y is equals to 0. So now we take all those that have got a dy dx on one side. So the one that have got a dy dx, which is this expression, and this expression on one side. So we end up having a dy dx, and factor out dy dx. So we're going to have 3x squared y squared minus the one with the dy dx minus x, then on one side. So the one that doesn't have a dy x, we take them to the other side. So we have got minus y, so we take minus y to the other side, is going to be a positive y. Then we take also 2x y cubed to the other side, is going to be minus 2xy. So for us to left with a dy dx, we need to divide by this expression that is attached to dy dx. So we divide both sides. So we end up having our value of dy dx as y minus 2x y cubed divided by 3x squared y squared is our final answer for dy dx, which is the derivative of what? Of our expression of x squared y cubed minus x y is equals to 8. Here is the second example, which says differentiate x squared minus y squared is equals to 8x. So when you check on our first term, which is x squared, is not attached to any variable, is only x. So we differentiate only in terms of x. So we're going to find a dx of x squared. Then minus, here we have got only y, the variable. So we're going to differentiate in terms of y. So we're going to find the dy dx of y squared. Then here we have got 8x. So we're going to find the dx of what? Of 8x. So when you differentiate x squared using the power rule, we're going to have 2, which is our power, times x to the power 2 minus 1 minus a. When you're differentiating y squared, you're going to get 2y to the power 2 minus 1, but we keep our dy dx. When you're differentiating an implicit function, wherever we're differentiating a y, we need to keep our dy dx. We don't remove it. So now we're differentiating also our 8x. 8x, we're going to get 8x to the power 1 minus 1. So this first term, which is 2x to the power 2 minus 1, is reached 2x minus our dy dx, 2y is equals to 8. So now we have to take all the constant that doesn't have a dy dx on one side, and we left with dy dx on one side. So when you take 2x to the other side, you are going to have 8 minus 2x, and we are left with minus dy dx 2y. So for us to remain or to left with only dy dx on one side, we need to divide by minus 2y on both sides. So when you divide by minus 2y, we're going to left with dy dx is equals to 8, is equals to 8, is equals to negative 8 minus 2x divided by 2y. Here is our third example of differentiating an implicit function. We have the question that is saying differentiate exponent xy is equals to exponent 4x minus exponent 5y. So when you're differentiating an explicit function that you've got a term with xy, we need to differentiate this exponent 2 times. The first we need to differentiate in terms of x, then we differentiate in terms of y. So when you differentiate in terms of x, we treat y as a constant. So we have got a dx of our exponent, we differentiate in terms of x, then you say plus derivative in terms of y of the same constant, because it has got 2 variables. So we say dy dx exponent xy. Then the second one, when you differentiate, we say is equals to, since the second term you've got only x variable, so we differentiate in terms of x. So we're going to have a dx of our exponent for x. And then the third one, which is also is an exponent 5y, it's only having a variable y. So we differentiate this expression in terms of what? In terms of y. So we're going to have a dy dx of our exponent 5y. So when you're differentiating an exponent xy in terms of x, we're going to treat the power of xy, we're going to treat y as a constant. So when you differentiate xy, you're going to get the result of y. Then we say our result, which is y times the original expression of exponent xy, we're going to get y times exponent xy. Then the second one, when we differentiate in terms of y, which is our dy dx of exponent xy, we differentiate the power, which is xy, in terms of what? In terms of y. So we treat x as a constant, which is going to be our result. So we're going to end up having a result of x times the original expression, which is exponent xy. Then the second one, which is the derivative of exponent 4x, we differentiate the power, which is 4x, and to get the result of 4x, which is 4. Then you say 4 times the original expression, which is 4 exponent 4x. Then the next one, which is the dy dx of exponent 5y, we differentiate also the power, which is 5y, in terms of y. So when you're differentiating 5y, you're going to get a constant 5. Then we say our result, which is 5 times the original exponent, which is 5 times exponent 5y. So now, whenever we're differentiating a y, we keep a dy dx. We don't remove our dy dx. So now the third step, we group all those terms that have got our dy dx on one side, and we group all those that have got a constant on the other side. So we end up having the dy dx one side, which have got an x exponent xy plus 5 exponent 5y, because we factor out our divide x. Then the one that have got a constant, which is 4 exponent 4y, then we take also the other one, which is y exponent xy to the other side is going to be a negative exponent y exponent xy. Then now we're left with dy dx. So to make dy dx the substitute formula, we need to divide each and every side by exponent x exponent xy plus 5 exponent 5y. We divide each side. So when you divide on the right side, we're going to left with dy dx, and when you divide on the left side, we're going to have our result as our dy dx is equals to exponent 4 exponent 4x minus y exponent xy divided by x exponent xy plus 5 exponent 5y as our derivative of our implicit function. Here are some exercises to test your knowledge and understanding. Use all the principles and formulas and methods that we have covered so far in our previous examples. Solve this question, find the derivative of each and every question, applying the appropriate differential rule on each and every question from question 1 up to question 8 to test your understanding. Thank you all for being part of Richfield Hybrid Learning Program. I wish to see you all in our next lecture.